Now let's talk a little bit about router switching functions, the encapsulating and de-encapsulating of packets. Primary function of our router is to forward our packets toward their destination. They don't all stay within that router. And this is accomplished by using a switching function, which we've already talked about. And that's the process used by a router to accept the packet on one interface and forward it out another interface. And a key responsibility of the switching function is to encapsulate the packet in the appropriate data link frame type for outgoing data links. So after the router has determined the exit interface using the path determination function, the router must encapsulate the packet into the data link frame of the outgoing interface. And what does the router do with the packet received from one network and destined for another? The router performs the following three major steps. It will de-encapsulate the layer 2 frame header and trailer to expose the layer 3 packet. It then examines the destination IP address of the IP packet to find the best path in the routing table. If the router finds a path to the destination, it encapsulates the layer 3 packet into a new layer 2 frame and forwards the frame out of the exit interface. That's what is shown here in this diagram. Here, PC1 is going to send a packet to PC2, and you'll see how it sends that packet from the PC through the routers to the destination PC. So PC1 says I have a packet for PC2. It says what path does it need to take. It looks at the packet's layer 3 data. It sees that PC2 is on a different network. And because it's on a different network, it has to encapsulate the packet and it sends it to the router on his network, and then it looks for the MAC address and then it sends it to the next router. That router is then going to look, open it up, see where it goes from here, and it'll eventually get to the correct location. Now that router 1 has the packet, it examines the destination MAC address, which matches the MAC address of the receiving interface, Fast Ethernet 00, and then of R1, and it copies the frame into the buffer. And then router 1 identifies the Ethernet type field, which means that the Ethernet frame contains an IPv4 packet in the data portion of the frame, and then router 1 de-encapsulates the Ethernet frame. And because the destination IPv4 address of the packet does not match any of the directly connected networks on router 1 is going to look at its routing tables to route the packet. Router 1 searches the routing table of a network address that would include the destination IPv4 address of the packet as a host address within the network. In this example, the routing table has a route for the network and the destination IPv4 address of the packet, which is a host IPv4 address on the network. The route that the router 1 finds for the address network has a next hop IPv4 address, which resides on router 2, and an exit interface of Fast Ethernet 01 on router 1. This means that the packet goes from router 1 out the FA01 interface to router 2. And because the exit interface is on the Ethernet network, router 1 must resolve the next hop of the IPv4 address with a destination MAC. So this is how it gets to the next hop. Next, that packet is going to be examined. At the MAC address, it says let me investigate it further. It's going to determine where it needs to go from here. It sees that the type and destination IP address needs to be forwarded. So it looks at its routing table, it finds where it belongs, and then it sends it through its serial 00 interface in this example so that it can reach PC2. So it rebuilds the information in the frame, and then it sends it on to router 3. So now our packet has gone from PC 1 to router 1. It found its next hop at router 2, and router 2 has sent it on to router 3. From router 3, the following process will take place. R3 copies the data link PPP frame into its buffer. It de-encapsulates the data link PPP frame, and then router 3 searches its routing table to see where that destination IPv4 address lives inside of its network. So the frame was sent because it's a point-to-point link, so he investigates it further. The router looks for the source IP, the destination IP. It sees that the destination IP address that's in the packet. It looks inside of its routing table. It sees that it needs to go out of its FA00 interface to reach PC2. Then it rebuilds the information frame, gives it the data2 data link frame, gives router 3's ARP information, which is its IP address and its MAC address for PC2, and then it sends it on to PC2. Now the routing decisions, we have to look at how the packet forwarding decision process. It's going to use one of 3 path determinations, either directly connected network, remote network, or no route determined. So there is a method to the madness. So the packet arrives at the interface. The router searches the routing table for a match. Does the destination IP address match the subnet? If it's directly connected, then it looks at the ARP table. If it's a remote connection, it encapsulates the frame and forwards it out of the exit interface to the next hop. Is there a gateway of last resort available? If there is, it encapsulates the frame and forwards it out of the exit interface to the next hop. If there's not, it drops the packet and it'll send an ICMP message back to the source destination to let it know that the packet did not go through. So best path. Best path is selected by a routing protocol based on value of metric it uses to determine the distance to reach each network. And a metric is the value used to measure the distance to a given network. Your best path to a network is the path with the lowest metric. And dynamic routing protocols use their own rules and metrics to build and update routing tables. For example, RIP, or Routing Information Protocol, uses a hop count. Open Shortest Path First, or OSPF, is cost-based on cumulative bandwidth from source to destination. And then we have Enhanced Interior Gateway Routing Protocol, or EIGRP, and that looks at bandwidth, delay, load, and reliability. So let's look at load balancing. When a router has 2 or more paths to a destination with equal cost metrics, then the router forwards the packet using both paths equally. So if multiple paths to a destination are configured on a router, the path installed in the routing table is the one with the best administrative distance. And administrative distance is the trustworthiness of that link. The lower the AD, the more trustworthy the route. So you can see here in the table, if it's connected, it has a 0 administrative distance because it is physically connected to the router. You have your static, your EIGRP summary, your external BGP, your internal EIGRP, IGRP, OSPF, ISIS, external EIGRP, and internal BGP. If multiple paths to the destination are configured,